In this video, we will be explaining and going through examples of special relativity.
Special relativity was introduced by Albert Einstein in 1905 to explain the motion of objects travelling at speeds close to the speed of light, or relativistic speeds, where classical Newtonian physics don't work. It's called special relativity because it's restricted to inertial systems. Hang on, what's an inertial system? It's simply a frame of reference in which all isolated bodies, not acted on by any forces, move with a uniform velocity, so really just non-accelerating. The theory of relativity is based on two principles, Einstein's postulates, which are as follows. The first postulate simply implies that observers in different reference frames, say one on the ground and one in a plane, observing any motion will experience the same laws of physics no matter what. The same rules and equations apply everywhere. The second postulate states that the speed of light in a vacuum, c, is a universal constant, the same for all observers. Keep these in mind for later, they're very important. Special relativity is one of the most popular topics in the history of physics, and yet one of the most confusing to introduce. But actually, when doing the maths, it's really just basic algebra. We won't bother you with any complex formulas in here. Except maybe this one. But we'll get back to that. Maths aside, this topic can be pretty counterintuitive. Like discovering the Earth is round when your entire life you knew it was flat. In this case, we're telling you that time doesn't flow uniformly onwards and isn't absolute. Here's a first example to show you how and why.
Consider a train, the old Relativity Express, zipping along at half the speed of light. The conductor, Albert Einstein, shines a pulse of light across the carriage, perpendicular to the direction of motion of the train. The train is passing through a station, and on the platform a cat is watching the train. As observed by our friend Albert, the pulse of light travels as seen here. Now, consider what the cat sees. If you concentrate on just the cat and the light pulse, you will see that the cat observes the pulse travelling along a different path, a longer diagonal line which we have exaggerated so it's not drawn to scale. This is the path that Einstein sees, and this is the path the cat sees. Through simple Pythagoras, even though this isn't to scale, here you can see that Einstein's path d1 must always be shorter than the longer path d2 that the cat sees, whatever the speed of the train. Before relativity, we assumed that the light pulse would be seen by both Einstein and the cat to leave the torch and arrive at the screen at the same agreed times. This would mean that the cat had seen the light pulse travel at a higher speed than Einstein had seen it move. But this would contradict Einstein's second postulate, that light travelling from an object should be observed to travel at the same speed by all observers, whatever their speed with respect to its source. If Einstein sees the light travelling a smaller distance than the cat does, then he must also, from the cat's point of view, have experienced a smaller amount of time passing between the light leaving the torch and hitting the screen, in order for the light to be travelling at the same speed c for both observers. Remember, speed equals distance over time. So, time has slowed down for him, according to the cat. This is known as time dilation, or the observed slowing down of the passage of time in one reference frame when seen from another reference frame that is moving with respect to the first. In relativity, perhaps unsurprisingly, in the same way that the passage of time between events can be experienced differently, distances would also appear different from moving reference frames.
This is an effect called length contraction, where the length of a moving body is measured as being smaller than its length at rest. The amount an object's length contracts by is given by this formula, where L is the measured length of the moving body from the stationary observer, L0 is the length measured from the object's stationary reference frame, and gamma is the Lorentz factor we saw earlier. This contraction occurs only in the direction the object is moving, so an object lying perpendicular to its direction of travel won't appear to contract. As you can see from this formula, when the velocity v of an object is small, the v squared over c squared term tends towards 0, meaning the length it contracts by is very small, and thus we don't notice this on a day-to-day basis. This is why relativity only really applies to objects travelling at relativistic speeds. Let's imagine our train going into a tunnel. Due to length contraction, an observer on the train is going to see the tunnel being contracted, as to them the tunnel appears to be moving. Similarly, an observer in the tunnel will see the train being contracted. Let's assume our train and tunnel have a rest length of 100 meters, and remember, the train is travelling at 0.5 c. The train will measure the tunnel as being 86.6 meters long, and the tunnel will measure the train as being the same 86.6 meters long. If we look at this from the train's perspective, the tunnel is shorter than the train, so the train can never fit inside the tunnel. But from the tunnel's perspective, the train is shorter than the tunnel, so it can fit inside. How can this be? How can the train be both inside the tunnel and not inside at the same time? Well, the answer is, it can't. To solve this apparent paradox, we have to realise that what one observer sees as two simultaneous events might not be simultaneous to a second observer, as each one is experiencing time differently. For the observer in the tunnel, a simultaneous measurement of the front and the back of the train show that the train lies inside the tunnel. However, those two measurements are not simultaneous for the observer on the train. They see the events happening at different times. First, the front of the train in the tunnel, then the front of the train leaving the tunnel, and then the back of the train in the tunnel.
To summarise, we looked at Einstein's postulates, including how light must travel at a universal constant, c. This led to some problems, which showed that time dilation and length contraction must occur. Finally, we looked at simultaneous events and how they're not the same in every reference frame. Thank you for watching our video.